All right, today we're going to talk about continuous random variables, different from the discrete random variables that we have talked about in class. If you have not talked about discrete random variables in class yet, I'm going to encourage you to hold off on watching this video until we've talked about it in class. All right, so I am looking on page 18. Go ahead and put the date up here at the top underneath this line right here. All right, so in this case, I want to take a number at random between 0 and 1. Any number can be chosen, okay? And I've put some examples there. Well, now this is different from an interval, like a discrete random variable, because literally any combination of number could be chosen. This is not something that I want to list out because guess what? We'd spend the rest of our time in this class writing out all of the numbers between 0 and 1 because there's infinitely many of them. We're not going to do that. So what we're going to consider instead is that this is a continuous random variable. This doesn't have discrete kind of levels, 0, 1, 2, 3, etc. This could be any number in a certain range. So let's define y to be the output. I want to know the probability that y is between these two values. Now all outcomes are equally likely. Okay, so we can't just assign each value to be like 1 over infinity because there's infinity number, that's 0, that doesn't exist. So in this case, we are going to assign probabilities using a density curve. And if you remember back from Unit 1 in Chapter 2, the total area under a density curve is 1, just like the sum of all the probabilities. So if I have a density curve where the area is 1, everything underneath that curve should add up to 100% probability. So I put the density curve over here. This would be the density curve for the example that we talked about, a number between 0 and 1. And I could find the area under the curve between certain values, and that's going to give me my probability. Does this sound familiar to you? Should. I have the definition of a continuous random variable there. It's going to take all the values in an interval of numbers. The probability distribution is defined as a density curve. And so what we're going to say is to find the probability of an event, you need to find the area under the curve and between certain bounds. Alrighty. Let's talk about mu and sigma again. This is mu, sigma, in case you forgot. Mu is the mean of the entire population. I was able to take everybody in my sample, have a census there, and I was able to find the mean. That would be the mean of the entire population. And then if you remember, it's X bar, that's the mean of a certain sample. So if we don't have everyone in our population, we call it X bar. We're going to talk mostly just about mu and sigma today. Sigma is a standard deviation of my entire population. And then if you remember, if you have just a standard deviation of a sample, we're going to abbreviate that with SD. And last thing that I'll have you recall from chapter 1, we can say that X is distributed normally with mu, comma, sigma. That's the notation that we use anytime we have a normal distribution. Remember, a normal distribution is a density curve. All right, let's take an example. The heights of young women follow closely to a normal distribution with mean of 64 and standard deviation of 2.7. So we're going to let y be the height. So I'll say that y is distributed normally with a mean of 64, a standard deviation of 2.7. And if I repeat the choice many times, the distribution of y is approximately normal, which is great. Okay. Find the probability of choosing a woman between 68 and 70 inches tall. We've done this before, you guys. All right, so let's find the probability that y is between 68 and 70. I can't do this yet because I need to standardize it first. So what we're ultimately going to be looking for is the probability that z is between certain bounds. So we need to figure out what those bounds for z are. So we'll take a z-score, which is the value minus the mean over the standard deviation. So we'd have the value is 68 The mean is 64. The standard deviation is 2.7. Value minus mean over standard deviation. Those are the z-scores of my bounds. So instead of looking for the probability that y is within certain bounds, I'm going to look for the probability that z is between 1.48 and 2.22. Let's draw our normal curve so we can keep in mind what this looks like. Here, this would be 0. We've standardized it. We have a standard deviation of 1 now, and I'm looking for the probability that z is between 1.48 and 2.22. So I'm looking for this bound here. Okay. So you'll have to remember how to find this. Now, the easiest way is to use your calculator to set the bounds for that with your calculator. If you remember how to do that, you're going to go to the statistics menu. You're going to go to distributions. So the distributions on the 8384 is above variables, DISTR. And then you're going to use normal CDF, setting your lower and your upper bound to be 1.48 and 2.22 respectively. You can also use the table. Just remember that it's always calculating the area to the left of the curve and that we'd have to subtract off the values at the end. You should be able to find this number in your calculator. Actually, I'm going to ask it on Edpuzzle so that you can make sure that you know how to find this, the area between the two curves. The value that you should have gotten is this. If you're not sure how to do that, definitely come see me or ask me on Zoom and I can help you figure that out. Okay, so let's kind of synthesize this. So we found a number and that's great and all, but like I said, I kind of like to wrap everything up in stats with a nice little sentence at the end. This is the probability of choosing a woman between 68 and 70 inches tall. So let's go ahead and use the same wording kind of here in the question, and we'll write a little summary sentence at the bottom. So I'm going to say the probability of choosing a woman between 68 and 70 inches is 0.0562. So I've got about a 6% chance of choosing a woman between those bounds there. All right, the problem on the next page that we're going to do that in class together. This is a discrete random variable, so we'll do that one in class. Let's look at the second try it that's on the next page, page 20. This is a continuous random variable here because we have this information about the y is normally distributed. We're looking at a professional tennis player, and he hits the ball extremely hard. So y is his first serve speeds in miles per hour. Okay, so what I want you to do is pause the video and see if you can answer part A. So you have the information about miles per hour, the mean and the standard deviation. Let's see if we can find the probability that y is greater than 120. And keep in mind that I will also ask you to kind of draw the normal curve and shade the area that we care about. Alrighty, I have my answer up there for you so you can check your work against mine. We're looking for the probability that y is greater than some bound. So you kind of have the option in your calculator. You can set the lower bound to be 0.83 and then set the upper bound to be something extremely high, like 999,000. Or you can take 1 minus the probability that z is less than 0.83. And you should get about 20.33%. All right, let's look at part B. Part B is exactly the same as part A, except now we've got y is greater than or equal to 120. It's going to be the same thing as part A. And here's why. What's the probability that the speed that Raphael hits the ball is exactly 120 miles per hour? Now, I'm not talking about 120.0000001 miles per hour. I'm talking about 120.000000000000000 ... all the zeros forever and ever and ever. That's going to be really, really, really unlikely. Is it not more likely that maybe we have a bunch of zeros, but there's a 1 thrown in there as well? Or it would be even 120.01. Those are not 120. The only way we can get exactly 120 is if we have zeros that continue on and on and on forever and ever and ever, which let me tell you, that is unlikely enough that it's not going to matter to the probability. So part B is the same as part A. Let's look at part C. We've done ones like part C before, but let's go ahead and look at it. We're looking for what C value, what speed would be 15% chance of occurring. So we're really looking for the probability that y is less than or equal to c equals 0.15. We're going to need to turn this into a z-score. And so I'm going to use a different value because c is not going to be the same. Maybe I'll use a. And what I'm doing is I'm looking for an area of 0.15. So this is where we use our inverse norm command. Still under that same distributions menu, but now you'll choose inverse norm. The area is 0.15. And if I draw my little normal curve over here, we're looking for an area of 0.15. And what value would be less than that for area? If you want to use your table, you're just looking for the numbers in the middle. You're looking for an area of 0.15 and then figure out what z-score corresponds to it. In this case, A would be negative 1.04. That's the z-score that we should get, is negative 1.04. So I need to plug that. That's not a speed, that's a z-score. So I'm going to use my z-score formula, C minus 115 over 6. So I'm going to use my z-score formula to solve for the value. And we should get, not x, I used c, I should get a speed of 108.76 miles per hour. There you have it. These are cumulative continuous random variables as opposed to a discrete random variable. You'll notice that it's really similar to things that we did back in Unit 1, which is good news, just to kind of bring some of that back and refresh your mind.